Ladies and gentlemen, welcome to our very first lab experiment in the Chemistry 252 class, Organic Chemistry 2. And the very first thing that we're going to focus on is something that we have talked about in lecture. I think you probably have watched at this point hours and hours and hours worth of lecture videos concerning alcohols. And why not? Why not do our very first lab with an alcohol reaction? So what we're going to focus on in this lab experiment is going to be the dehydration of cyclohexanol. And I hope at this point you would know what dehydration is all about, because really that's very often the purpose of the lab, to support lecture topics that we present in lecture, so that way you can put a real life look at these reactions as they happen in person. The problem, though, is if you're doing this as a fully internet course, how are we going to bring the lab to you in organic when many of the reagents that are necessary for organic chemistry are highly carcinogenic? You shouldn't be touching them. You shouldn't be smelling them. We can't ship them in the mail. These are the issues that we have with organic reagents, and that's why you do not have an organic laboratory kit that we can send to you at your house, so that way you can do these things in the privacy of your own home. Otherwise, you would probably get arrested. Okay, so let's talk about the dehydration of cyclohexanol. So before I go any further, let's just review. Let's kind of pull back some of that lecture material stuff that we should know at this point, and let's prep ourselves a little bit for what this reaction is going to do. So the very first thing that I want to mention is the term dehydration. Do you remember what that means? Well, I hope that you're going to tell me it removes water. Okay, so we're going to have an alcohol, and the lab told me what alcohol we were using. It said cyclohexanol, didn't it? It says the dehydration of cyclohexanol. Okay, so that means I should be taking this alcohol and I should be dehydrating it. Well, let's start with the structure of cyclohexanol. Cyclohex means a ring, cyclo, and hex means 6. All right, so 1, 2, 3, 4, 5, and then 6 down here at the bottom. Anywhere on here, folks, it doesn't really matter where you put the OH group, because that will automatically be carbon 1. And we normally leave the 1s off in the nomenclature system. So cyclohexanol is this 6-membered ring with an OH. So in this reaction, at this point, if you've made it this far in lecture, you should know how to dehydrate alcohols. We've talked about a couple of different ways to do it. Can you think of one? Well, that's what you're going to find out in this lab experiment. You're going to figure out what kind of reagents we've chose to use. There's a couple of different variations and versions out there, and we're going to dehydrate. Okay, so dehydrate means I'm going to take this alcohol group and whoop, there it goes. It goes bye-bye, bye-bye. Now, do you remember what happened when we removed the alcohol group? Something has to go on with this structure. So that's what this lab is going to walk you through, because at the very end of this, we are going to take a look at the product that we have formed, and we're going to confirm that we have formed that product, which proves that this reaction goes forward the way that we have discussed in lecture. All right, so without wasting any more time, let's take a look at the lab procedure. So in this lab folder, you are going to find a document that looks like this. And this is our lab procedure that we're going to walk through together in this experiment. Now, the problem here is that they give me a couple of different options to do this laboratory experiment. They give me what we call micro scale, and then they give me something that's called semi-micro scale. All right, so we're not going to do the micro scale. That's like little bitty tiny little flask. for poor little labs that don't have a lot of money to purchase equipment and glassware and reagents. We're going to do this semi-micro scale instead. So as I scroll through the lab document, they're going to give me a little bit of background just to kind of ding ding refresh in my head what we've discussed in lecture. And it looks like they are setting up the elimination reaction. They have a whole section on this. So dehydration is somewhat like an elimination. It looks like, if you remember from lecture, we're going to have a group that's going to go away, and then the neighbor carbon is going to also donate a hydrogen, and this will form a double bond in between the two carbons. So this gives me an idea of the type of product that I'm going to have in the end. So they give me a few examples just to say, hey, remember, this is the stuff that you talked about in lecture. You had this OH group, and this OH group becomes protonated, and that protonation probably came from an acid. And then this group ended up leaving to make water, and we had a neighbor carbon that donated something like a hydrogen, dehydrohalogenation, or dehydro as far as water goes here, not halogenation. That would be a halogen, a chlorine, a fluorine, a bromine, an iodine. So they go through this whole background, and I'm not really going to go through that. We will do that in little bits at a time. I need to find the lab procedure, though. So here on this page, this is where the lab procedure is going to start. So number one, if you would like to follow through with me as we go through this lab, it says using distillation to dehydrate the cyclohexanol that we are going to be using together. So here it says assemble the distillation apparatus shown in figure 5. Okay, so here's figure 5, and this is what I need to set up in the lab. So we'll do something similar to that, not exactly, but we'll do something very close to that. Then it says, if necessary, use substitute glassware as directed by your lab instructor. Well, what do you know? I just told you that, didn't I? All right, so it says remove the 10 milliliter round bottom flask. Well, that's one of the things that we are not going to be using is a 10 mil round bottom. We're going to use something a little bit bigger. And then it says place 4 milliliters of 85% phosphoric acid, which is really concentrated phosphoric acid. It doesn't really go higher than that quite easily. And 2.84 grams or 3 milliliters of cyclohexanol into the round bottom. So that's my first goal. I'm going to take the cyclohexanol in the lab. I'm going to mix it with phosphoric, and I'm going to put these two things together into what they call a round bottom boiling flask. All right, so here is the cyclohexanol that we are going to use together in this lab experiment. I like to take pictures of the bottles because later on when you start writing a lab notebook, this kind of material is going to be important. And the reason is because here on the label, you're going to see the manufacturer of this chemical. And on the label on the other side, you will see things like lot numbers, and you're going to see that right there, kind of off to the side. You don't need it for this lab, but I'm prepping you up for some of the others that you'll see in the semester. You'll also see the structures and the formula weights and other pertinent information that you might need throughout a lab experiment. So this is a picture of the cyclohexanol that we're going to use. Now, I will say that this bottle's been around. This bottle is probably older than I am, and it's almost empty, which means I get to order new and fresh, and I like when that happens, but it's still going to probably work for us. So we will use this cyclohexanol, and we'll see what it does in this lab experiment. So this is my first reagent, and there's my alcohol. Now, the lab directions then said, take some of this phosphoric acid. All right, so here's a bottle of phosphoric acid. It is concentrated, and here you'll see the word concentrated, and you'll see about 85%. So there's proof that we are using the proper phosphoric acid as far as the reagent goes. Okay, so I'm going to go back to the lab procedure. There's the two reagents that I need in the beginning, and then it says add 5 drops of concentrated sulfuric acid to the flask and a magnet. And then we're going to stir this, and then we're going to heat it. So this is the setup that I'm going to have to put together before I mix these two things together, right? Okay, so here's the picture of the real pieces that we will be using to set this system up. So a couple of things that I want to do here, because depending on who you are, you might not have ever worked with this type of glassware. If you've had me for Chem 251, whether online completely or in a hybrid course, you have used these pieces of glassware before, but I'm not going to make any assumptions. So we're going to go through and we're going to talk about what these things are called. So here in these two kind of long pieces of glass, this is called a pipette. A pipette. All right, so a pipette is used in a lab to measure out very specific volumes of liquids. So on the pipette, we are going to be using probably a 4 and a 3. And the reason is because that's what the lab directions told me to do. They told me to measure out that amount of volume or milliliters. So I'm going to go to our drawers. I'm going to pull out these pipettes. And the way that you use these is you literally stick this into solution. There's a bulb, and that's the bulb over here to the left-hand side. This goes onto the top of the pipette, and you literally suck up the solution into the pipette. Now, in the next picture, I'll come back to that one in just a second, I did a close-up here. And this close-up is showing you here at the very bottom that there is a marking on the pipettes. And that means you suck the solution up until you get to that mark. When you get to that mark, then you have exactly 3 milliliters in that pipette. And then you can deliver that volume into a reagent container that you need to use at that point. So these are much better than beakers. They're much better than graduated cylinders. They are much better than Erlenmeyer flask. And quite honestly, folks, we hardly ever use those to measure any type of volume with in a laboratory. Those that tell you to use that type of glassware to measure out things, they probably have not invested some money in using the real stuff that real people use at real companies, and this is the stuff that they use. They're very expensive volumetric pipettes that could cost $30, $40, $50 a piece. So with our laboratory, the Chemical Technology Lab, we have probably at this point $10,000 to $15,000 invested in volumetric pipettes. All right, so there's number one. That's going to be our delivering device. What you're going to see here is keeping track of temperature. So this is a thermometer that you're seeing in this adapter, and this adapter is just made to fit on the joint of the glassware. So we call this 2440. This gives me a size of the width and the length of that joint, basically. That's what that number means. So all of our glassware that we use are 2440 joints, which means that as long as we order 2440 joints, we can order glassware that will fit and connect together like a stack of Legos. So this is a number that we often use. This is not micro scale. It's probably not even semi-micro scale either. This is normal standard glassware. Again, very expensive, but folks, we have tons of this type of glassware in our lab ready to go. So here's an adapter with the thermometer. This is going to be called a side arm adapter, if that's what you want to call this. That's perfectly fine. You can see why they call it a side arm, because on the side we have an arm. Oh gosh, no one said organic was rocket science, and look at there, they made your job easy. All right, so here we have the side arm adapter, and the purpose of the side arm adapter is that this thermometer piece will go on the top of that adapter, and it will fit in there quite nicely. All right, down here at the bottom, you see that joint as well. Here's another joint, and that's the purpose of the boiling flask. So here's the round bottom, round because it's round. There's our round bottom boiling flask. So that's going to connect here at the bottom. My thermometer will be connected up here at the top, and this side arm piece will go into what we call this big long piece of glass up here at the top, a West condenser. All right, so this is a West condenser, and the purpose of the West condenser is to condense. Oh, go figure. Well, what does condense mean? It means it's going to take a gas and it's going to condense it down into a liquid. Well, that liquid is going to trickle all the way down this West condenser, and as it trickles off the end, it goes out this spout, and this spout is going to be called a drip adapter. All right, so a drip adapter is adapting onto the West condenser, and it takes the liquid and it sends it through a narrow little piece of tube, so that way you can collect this much easier. So these are our glassware pieces. This is what we're going to use, and we are going to assemble this very similarly to what we did here, what they were showing us to do here. So here's our round bottom. You can see that. That's where all of our solutions are going to go. There's the side arm adapter. They're calling it a distilling head. It's kind of the same thing. And then here's our thermometer adapter. You can see that piece there with our thermometer. Here's our condenser. Notice that there's water out and water in. Water always goes in from the bottom, and then it circulates and pushes all of the warm water through, and then it comes out the other end and down into our sink. And then here is, they're calling it a vacuum adapter, but we do have those. We're just using a simple drip adapter instead. And then a receiving flask. The problem here, though, is that the receiving flask is quite large. We're not going to be getting a lot of material. So instead of a receiving flask, we're just going to use a test tube. We're not going to fill a test tube full of product. That's how little of a product that we're going to get. So a test tube is going to be perfectly fine with that system. All right, so there's another close-up of that pipette at the very end. Instead of a sand bath, again, this is for very cheap, skanky labs, and we have a better stocked full lab. So instead of a sand bath, what we have ordered for our lab stock that our students get to use are things called variac heating regulators or transformers. So basically this box is to take the energy from the outlet and provide that energy to something that we call a heating mantle. And this allows me to control how hot that heating mantle will actually end up becoming. So in other words, think of this as a stove eye. And you can turn the stove eye hotter in order to get your stove to cook faster. And that's exactly how the variac works. This is our stove eye that we will use, and we will use this to heat our heating mantle, and we have control of how fast or how slow or how hot that those things can get. So I've not really showed you a picture of the heating mantle yet, but here is a larger view of the lab counter that we're going to be working with. And you can see the heating mantle here. So first, over here to the side, this is our variac transformer. It is plugged up into our outlet, and you'll see that here. This variac then is connected to our heating mantle, which is right there. This solution is going to have to be stirred over time, so that's what you're seeing here at the very bottom. This is a stirrer that we will cut on, and there's a magnet that will be inside the flask, and it will constantly stir that solution for us, so that way we don't have to worry with it. Here's our volumetric pipettes, our volumetric pipette bulb. You see all of the pieces of glassware back here on the side, like our thermometer adapter, the side arm, the West condenser, the drip adapter, and then over here to the left, these are our reagents. So the reagents, cyclohexanol, you've seen that jug already. Here's our phosphoric acid, so now you've seen that jug, and then a catalyst. And the catalyst that will be used in this experiment, folks, will be H2SO4. So H2SO4, that is sulfuric acid. Now, when we talked about dehydration in lecture, we said that sulfuric acid can just be used and that's it. But this lab is going to show you that dehydration can be used with a different acid. We mentioned this in lecture. We said sulfuric or phosphoric. But then they quickly, especially in the textbook, went straight to sulfuric only. So this is just to remind you to say, hey, listen, we told you there's more than one way to do a dehydration. And we mentioned phosphoric, and then we quickly went to sulfuric, and that's the only thing that we talked about at that point. But phosphoric will be able to do it too. All right, so there's all of the pieces. They are getting ready to be assembled together to give us that diagram that we see in our lab directions. If I go back to the lab directions, it says once you put everything into the boiling flask, reattach everything together, turn the water on, turn on your magnet stir, and then heat the reaction while you stir it until the product starts to distill. So that's going to tell me we're going to heat this up, and then sooner or later we're going to get some vapor that will come up through here. That vapor will then be able to travel onto the sidearm piece. The cold water is going to hit it, and then that liquid is going to drip, 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 drip into my receiving flask over on the right-hand side. Okay, so that's the process of distilling. And it tells me you continue to distill until you get to a temperature, and that temperature is 85 degrees. Then you cut everything off, and you are done with the synthesis step. All right, so this seems pretty easy. I add my stuff, I turn the stirrer on, I turn the heat on, this stuff will evaporate, then it will condense down, and I'll collect it. And I'll just let that go on. I don't have to do anything to it until it gets to 85 degrees. All right, so pretty straightforward. Not a lot to this, right? No one said organic reactions were hard. It might be hard to memorize, but they're not hard to do. All right, so here I've got a video, and this video is going to show you the process of adding cyclohexanol and the phosphoric acid. All right, so let me hit play, and we'll just narrate as we go. So what you're seeing here kind of out of focus is our heating mantle, and then here on top is our round bottom boiling flask. And here's our lab technician, and she's getting ready to add some of the, well, first the magnet. The magnet's going to go in, and then she's going to add the phosphoric acid. So the lab directions told her you need to be very precise with your volumes. So here's the 4 milliliter volumetric pipette, and that pipette is going to go down into the phosphoric acid jug. Now, normally we don't let students do this because you can contaminate, but you know, we trust ourselves. She's been doing this for years, so she can pipette directly out of the container without a problem. So 4 milliliters into the pipette. She's looking at the level, the meniscus, to get it on that line that I showed you. And now that 4 milliliters is getting added into that volume, or into that boiling flask. So this takes a little bit of time. It's not just going to flood out. It's going to take some time to drain that liquid out of the volumetric. So this normally takes about 30 seconds or so, depending on how thick that liquid is. So she's looking at the volume in the pipette, and she's saying, okay, well, at this point, it looks like it's all out of there. So she's put the lid back onto the jug, moved it away, so that way she doesn't knock it over and create a huge, big, nasty spill in her lab. No one wants that. And then she's getting ready to pull that volumetric pipette out of the boiling flask. All right, so here it goes. And then the next step in the lab procedure was you add your cyclohexanol. So that means that in this next step, she's going to have to take this volumetric pipette once again, and this time she's going to pipette the cyclohexanol. So do you remember what that volume was? Do you? Do you remember what the volume was? Well, I hope that you told me 3. All right, so 3 milliliters. That is what we need here for the cyclohexanol. So she's taking the lid off the cyclohexanol at this point. There's the 3 milliliter volumetric pipette. So in the bottle it goes. Normally you wouldn't do that, but she can. And then she's sucking up that cyclohexanol until she gets to the marking on the volumetric pipette. So she's looking at the line, she's slowly draining it, making sure the meniscus will go to the line of the pipette. And then she will deliver that 3 milliliters into the round bottom flask. So now we've taken our 2 reagents and we've mixed them together. We have our cyclohexanol, which is the alcohol, and now we have our phosphoric acid, which is going to be the reagent needed to dehydrate the cyclohexanol. But we're missing a key ingredient, and that key ingredient has not been added in. What is that key ingredient? Do you remember what that third component was? Well, I hope, because we just talked about it in a couple of slides ago, that other ingredient is going to be sulfuric acid. Now, in the lab directions, it doesn't tell me to pipette. It just says adds a couple of drops. That's all that you need for the catalyst. You just need to add a couple of drops of sulfuric acid into this round bottom flask. And that is it, folks. We don't even have to measure it. All right, so before we add the sulfuric, I just want to give you a different view of adding the phosphoric acid here. All right, so this is a little bit closer up, and you can maybe see that addition a little bit better. The video is not as long, but this is just a different perspective of adding that solution into that round bottom. All right, so there's the pipette here in the back, and then that liquid is getting drained into that round bottom. So this is the proper setup. It's very important to be very specific, because guess what? At the end of this lab, they're going to ask you to calculate theory yield. And if we are not very specific in the beginning about the volumes that we decide to use, we cannot calculate theory yield, or we will not be able to provide a value or a very good value. The same thing's going to happen here as far as our cyclohexanol goes. That should be cyclohexanol, not cyclohexane. So that is my mistake. But there's the cap that goes on, and again, the addition of the round bottom there in the back. All right, so the next step is going to be the sulfuric acid step, right? If I go back to the lab directions, it then says up here at the top, add 5 drops of concentrated sulfuric. So it doesn't have to be exactly 5 drops, but it gives you an idea. Not much at all is actually needed in this process. So this is slightly fuzzy in the back, and I do apologize for that. But she is getting ready to get the sulfuric acid, and you will see that. So here's the sulfuric acid jug. There it is. So we keep it in smaller bottles because it is a hazard. And she's getting ready to add that sulfuric acid into that flask in the back. All right, so here we go. Just a couple of drops. That's all that's needed. Just a couple of drops. And there they go. And the reaction has now started. Folks, was that hard? Well, no. Organic reactions, organic labs are not hard. That's all there was to it. So those 3 reactions have now began a reaction. And that reaction is a dehydration reaction. All right, so here's a picture of the initial start of the reaction. So this is what it looks like. Notice that all of those solutions were clear. Every single one of them were clear. But folks, now look at this color. There's something that's happening in that round bottom. We're getting an observational change here. So this is at the beginning of the reaction, and we need to continue this reaction forward until we start getting distillate, and until we start collecting product, and until it gets to 85 degrees. So at this point, we have cut on our variac transformer. The variac setting in the beginning is a 50. So we cut it on a little bit slower, a little bit lower in the beginning, just because this thing's a jacuzzi. And we're going to have to get all of the members to know each other before the night goes further. So we keep it at 50 just to get everything kind of loose and acquainted, and they know each other at this point, and then we'll crank up the heat a little bit later on them. So once again, we're going to have to think about what kind of product is probably formed. What's the boiling point of that product? Why are they telling me 85 degrees? And all of the lab is going to tell me this information. And I'll show you where to find that in just a second. But before I do, here is a video of basically the beginning of the experiment. So our magnet was stirring there in the bottom, as you could see. It became an orangey, golden, amber color. And here's our thermometer. And she's going to zoom up so you can see that temperature. It will come into focus in just a second. The camera's horrible about focusing, but it looks like it's below a 40. So we got way to go before we get to the 85 degrees. Now the question here is, why on earth 85 degrees. Why does it keep telling me 85, 85, 85? Is it a made up number? No, it's not a made up number. And here's why. We have just taken cyclohexanol, which is this compound, and we have reacted it with H3PO4 with a little bit of H2SO4 as a catalyst, otherwise known as H+. Well, we know from lecture that a dehydration is getting ready to happen. All right, so I'm going to start like I do in lecture with our reagent. And with this reagent, folks, we know what is going to happen. The phosphoric acid is going to come in, and the sulfuric acid will come in, and bam, the OH group. We're going to give it a black eye. We're going to make it ugly. All right, so the H from the acid will go onto this group, and this turns into water, which is a very good leaving group. So this allows the alcohol to be extremely, extremely ugly. And that molecule wants it off. I don't want this OH anymore. It's too ugly. I can't even look at it. But if that OH leaves, then this carbon's going to go through the ringer because that carbon is going to be shortchanged. So the buddy for carbon, like we talked about in lecture, has a hydrogen on it. So that buddy is going to come and fork out some bail money, and it's going to go, okay, carbon, listen, I got your back. Don't worry, I'm here for you. So it's going to donate a hydrogen, which regenerates the catalyst, by the way. And then this OH group is going to disappear, and there is our dehydration. So we have just removed water, and now these two carbons can share extra bonding time. A little bromance has happened between those two carbons. So we form a double bond at this point. So this product, as we can predict in lecture, is probably going to be cyclohexene. At least we hope it will be. And I know this because I know a little bit of background about organic reactions and dehydration at this point, right? So if I go back to the lab directions and we start looking at some information that they give us, it looks like cyclohexanol's boiling point is 160 degrees. That's normal. You know, these are alcohols. Alcohols are polar. Alcohols can participate in hydrogen bonding. All of those are intermolecular forces that increase the boiling points of these compounds. Cyclohexene, though, cyclohexene does not have any of those properties going for it. I hate it for cyclohexene. It just doesn't. I'm sorry. So cyclohexene has a boiling point that's very low, at least lower than the alcohol version. And that boiling point is 83. So that is why they tell me in these directions, stop everything at 85. Once you go past 85, folks, if you get any type of liquid at all, it's probably not going to be cyclohexene because cyclohexene has already came over as a vapor, condensed, and dripped down into my collection tube. So this is why 85 is such an important temperature for them as far as the lab procedure goes. So that's what I needed to say about the reaction and why they're telling you to do things throughout this reaction. So we heat. We're about 30 minutes into the process at this point, and here's a video that shows you kind of midway through. So take a look at that solution, see what it looks like, see if there's any more observational changes that you can pick out. And there's the reaction flask about midway through. The stir bar's in there stirring it. You see the condensation up. And then here's our temperature readout, and she will pull back a little bit and it will zoom in. And you will notice that we're still pretty far away from the 85 mark. All right. So that condensation was in the flask. The condensation was in the neck, the side arm. So we knew that this condensation was eventually going to make its way over to the West condenser. So now that we know everything is moving, everything is grooving, we cut the variac up a little bit more, and that's at 70 now. So this has nothing to do with temperature though, folks. I want you to know that. This has nothing to do, that does not mean 70 degrees. That means 70% of what the variac can supply to the heating mantle. All right, so this will go on for another 30, 45 minutes. So we're waiting, and you're looking at your time on the YouTube video right now, and you're looking at 34 minutes. So I want you to understand that you would be even longer in the lab if you had to do it on your own. So we're saving you some time by doing these extremely long videos on organic lab. So let's take a look at the last part of the lab experiment, and here's at the very end of the reaction. Folks, look at this flask. I hope that you can tell me an observational change that's happened right now. So I'm going to hit the video, and you will be able to see this in motion at the end of this reaction. So there it goes. You can see the condensation's made its way all the way up. We'll pull back a little bit so you can see the temperature. And here we're a little bit above the 70, but we're still way below the 85. So that means I need to keep collecting. I mean, this stuff is not done. And you can see the condensation here on the sidearm, and that is turning into a liquid down the west condenser. And we are getting liquid drip, 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 drip over here in our test tube to the left-hand side of us. So we're going to keep collecting this until we get a temperature of, ding, ding, 85. So there's the cutoff temperature. Everything else, folks, we're not going to keep. Anything else that comes over after 85 is not the product that we're after. So this is the end of our process at this point. That's all it was. That was it. All of these hard, nasty mechanisms and reactions in lecture has basically boiled down to about an hour to an hour and a half of let's mix these three things together and heat it up. That's all that there was to it. All right, so just to show you that we did collect product together, this video is going to show you a couple of very slow drips and see if you can catch one of the drips that comes out of that drip adapter. I know that you'll be able to do it. I'm going to be quiet. Oh, did you see it? If not, rewind the video and play it again. It's in there. So this product did not drip over very fast, and that's okay. No one said that it was going to. We just kept collecting until we got to that point. All right, so 85 degrees has been met, and now we move on to the next part of the lab procedure. All right, so the next part of the lab procedure says remove the receiver flask. Okay, well, that's our test tube. And use a Pasteur pipette, a Pasteur. Always say it that way because it makes you sound really fancy. Pasteur pipette to transfer the distillate into a centrifuge tube or a small test tube. Well, we collected it in a test tube, so we were smarter than the lab directions. So now we can move on to the next part of the lab experiment. All right, so the next part says we now have probably made cyclohexene, and now we need to isolate it. Isolate means get it by itself. What? Get it by itself? I thought there was nothing else left over. No, we didn't ever say that. We said that cyclohexene will boil at 83 degrees. We're going to collect everything up to 85 degrees. There could be a chance that some stuff came over before the 85 degrees that wasn't cyclohexene. So it says, notice that as the distillate in the tube cools down, 2 layers will form. 2 layers? Well, that means that one of those layers is actually something that we want, and that's cyclohexene. And it says, use the Pasteur pipette to remove the majority of the bottom layer, and then place the bottom layer into the container labeled recovered acid. Oh, I see. So that extra layer is acid that maybe found its way over into that collection test tube. So if we do see 2 layers, that is what that second layer is going to be. Now, if I go back to these directions before I show you kind of the next step that we did, it says dry the top layer by adding 0.25 grams, give or take a little bit, of anhydrous calcium chloride to the test tube. All right, so let me tell you a little bit about calcium chloride. In organic chemistry, water is going to be a very big problem for us. in all of these labs, water is going to be a burden because water and orgo, folks, do not mix. I mean, these two things have never gotten along, and they never will. It's like a really strong, hard-headed Republican and a really strong, hard-headed Democrat. They will never see eye to eye, no matter what kind of arguments that you give them. You're fighting a losing battle. You might as well just give up. So water and organic are very similar. No matter how hard you try, very often they will never mix together. So we have to remove the water in these reactions, and you're going to see that throughout the semester. So these are going to require what we call drying agents. And drying agents will suck up the water. That's what they do. And one of the drying agents that we use in a lab is calcium chloride. So that is why this lab procedure tells you to kind of do this. Weigh out some calcium chloride, put it into that organic layer, and dry it. So this is going to absorb any water that you left behind. We're just doing this as an extra precaution step. That's it. So it says let the test tube stand for 5 minutes. And when you let that test tube stand for 5 minutes, we're going to then weigh a clean sample vial. So we're going to tear it out, make it read 0. We're going to transfer that organic into that vial, and we're going to get a new weight, a new mass. So that's what they tell us here. Weigh your product. That way we can figure out how much product we have ended up with at the end of this process. How good were we? You know, of all the transfers, and we didn't hardly do any, and the distillation process, did we get everything over into that receiving flask? How good were we as far as percent yield goes? That's one of those questions they're going to ask for us at the very end of this lab experiment. All right, so let's go back to here. It looks like now that I've collected my stuff, I need to grab some calcium chloride, and there's our bottle. That's our drying agent. Notice it says anhydrous. What does anhydrous mean? Oh, it means without water, anhydrous. So I'm getting ready to put it in water, so it will no longer be anhydrous anymore. All right, so there's the front of the calcium chloride bottle. Again, to prep you for future labs when you have to write lab books. Here's the side of the label. Calcium chloride, our lot number, our CAS number. The lot number's down here at the very bottom. Anything you ever know that you want to know about calcium chloride is very conveniently placed on the label. I'm going to open up the jar, and then here you see the calcium chloride pellets. So they're like little bitty white rocks. Nothing special, nothing fancy. So we need about 0.25 grams. I mean, that's what the lab directions told me, right? So here's the balance, and it has been tared. So it reads 0.0000. I'm going to put a weigh boat on it. And this weigh boat now has some weight. So we're going to tear it out once more, just so we can get that to read 0.0000. And then we'll add some calcium chloride to that weigh boat. And we need about 0.25 grams. So what we've ended up here is 0.2545. So super, super close. That's what the lab told me to do, and that's what we'll add in. All right, so here's our laboratory technician, and she is showing you the product that has been collected. Notice that down here at the very bottom, you might see some disturbance between the two layers. That disturbance is what they're talking about. Do you see that? It's right here. You see that meniscus there at the bottom of the test tube? So this is a very good sign that all of this up here is going to be our product, and that is cyclohexene. And then down here at the very bottom, this is probably water, because they told me take something, some type of dropper, which is this thing, stick it down into solution, and suck the water up using a Pasteur pipette. That's what that is. Suck that water out and get rid of it. And that's exactly what she did. Then after you do that, you could still have a little bit of water left over, and that is when we add our calcium chloride pellets. So that's what we're seeing here in the picture. The calcium chloride 0.25 is a sucking all the water up out of that organic layer. So that way we are ready to do some testing on it, because we're going to have to prove that this is cyclohexene. And there's a couple of ways that we can do that. All right, so before we do that, it told me in the directions you're going to have to get a mass of the product that you recovered. All right, so take a sample vial, and that's what we did here. There's our sample vial with a lid, and that is 7.8034 grams. So the balance has been tared. This vial has went on it, and that vial with the lid is 7.8034. So we'll take the Pasteur pipette and we will deliver that volume into that container. And when we do, the cap goes back on. You can see that liquid. It's right there. You can see it. It's right there at the bottom. There's my cyclohexene, I hope. And that mass is now 9.0791. So 9.0791 is the product plus the vial plus the cap. And just the vial and cap alone is 7.8034. All right, so now let's go back to our lab procedure. It's going to go through and it says, okay, clean it up. Don't leave the lab disgusting and nasty, because we're not your mama and we're not going to pick up after you. All right, so now we keep going on, and it's going to tell me a way that we can go through and check to make sure that we have actually made cyclohexene. All right, so as I scroll through the lab, it's going to tell me that toward the end, and it has here product characterization. So how do we do this? Well, there's one test that we're not going to do, and that's number 1. Number 1 says using ammonium cerium nitrate to test for alcohols. Okay, this we're not going to use. It's a weird little reagent that we only really need for this lab only. We never use it for anything else. So why waste taxpayer money that we get from the state to purchase a reagent that we're only going to use one time? So we're not going to do it. We're not wasteful like that. And because of that, we are skipping test number 1. Okay, so now we go to test number 2. Test number 2 says using bromine to test for alkenes. Huh? Okay, let me kind of clear this up a little bit. Look at what you've made. What you have made is cyclohexene. Okay? Cyclohexene is an alkene. An alkene means double bond. That's what you've learned from Organic 1. Over to the left-hand side, you started with cyclohexanol. Is that an alkene? And you're going to say, no, it's not an alkene. And the reason it's not an alkene is because there's not a double bond there. So this test is a test for alkenes, which means if I did make cyclohexene as a product, and that product is what it should be, then that product is an alkene, and this test will tell me that an alkene is present. That is why we do this test at this point. So this test is pretty easy. Label 3 small test tubes, cyclohexanol, cyclohexene, and the product. Place 2 drops of your cyclohexanol into tube 1. Place 2 drops of cyclohexene that you know is cyclohexene into another test tube. And then place 2 drops of your product in the third test tube. All right, that's not a big deal. That's pretty easy. And then it says add 20 drops of dichloromethane to each test tube and stir them up. And then finally, you add 2 drops of Br2. That's bromine, liquid bromine. The stuff that will turn into a vapor at room temperature, and I can breathe it in and give me chemical pneumonia, and I can go to the hospital. If I breathe in too much, it will actually react with the moisture in my body, in my throat, in my mouth, in my eyes, in my nose, and it can set up hydrobromic acid. I could actually start making acid inside of my body if I begin to sniff this bottle, and that's something that we don't want to do. All right, so this test seems pretty easy, right? So let's take a look at the setup. I'm going to be talking about the bromine test. All right, so here's our very first identification test. I'm going to take cyclohexene. So here's cyclohexene, which should be my product. And I'm using this because this is a stock and it's a standard. So I know this is cyclohexene. It is an alkene, therefore it should also react. So that's why we're using this. I'm then going to go back and take cyclohexanol that we started with, that bottle. You remember what that bottle was. It was the very first slide that I showed you. And then we're going to take something called methylene chloride, and my product, by the way. But methylene chloride you have also seen. Methylene chloride is abbreviated MECl2. All right, so MECl2, methylene chloride. This is the common name for this reagent. It is used all the time in organic. And if you remember from Organic 1, very often we were using what I would call carrier solvents, things to keep things in solution. And this was DCM. Well, DCM stood for dichloromethane. So this is more of an IUPAC name that this reagent goes by. Well, there's the jug, folks. I mean, it's real life. There's the jug. So this solvent is going to be needed because I'm getting ready to put bromine in solution, and I do not want that bromine to escape. I want that bromine to stay in solution, and methylene chloride does a very good job for that. So let's talk about theory. Let's talk about what's getting ready to happen. In Orgo 1, what you should have taken away from that course is that I could take an alkene, so here we go, just a random general alkene, a double bond, and I can add bromine to it with some DCM. Do you remember that now? Oh, this was a reaction that we had to learn back in the day. This was from Orgo 1 class right here. And we're getting ready to do that reaction, folks. So it's a real life thing. This is what we're getting ready to do. If they did not write DCM here, they could have wrote MECl2. It was the same thing. And if they didn't give you that, they probably gave you CH2Cl2. All of those were identical. It's just different ways to represent the same stuff. So in this reaction, if you go back and remember from Orgo 1, I'm going to redraw my starting reagent. There we go. And this was an electrophilic addition reaction. So bromine comes in and the double bond, and two sites of attachment open up here and here. Well, bromine goes on one and bromine goes on the other. That's how this reaction works. Well, it's okay because we have cyclohexene. That's still a double bond. It's a ring, but it's still going to work. There's no difference in this. So this double bond will react with Br2 with some carrier solvent, and that double bond will break, and two sides of attachment will open up, and bromine goes on one and bromine goes on the other. All right, so this is why this is so important. Br2 is brown, reddish brown in color. I'm going to visually see that. But when Br2 goes breaks and it goes onto the carbons in the double bond, this is no longer Br2, is it? These Brs have been separated. Well, when the Brs get pulled apart, no longer are they attached at the hip. Well, they change into something different. That's kind of like real life, too. Two BFFs attached at the hip, and now you rip them apart, and they grow up, and they live their own life, and they become a little bit different than what they were in high school. So this Br2, because it's not together, folks, the color goes away, and this is colorless now. So what we're going to see, hopefully with this reaction, is that when I add Br2 to cyclohexene, my red color goes away. When I add Br2 to the alcohol, that alcohol is not an alkene. That alcohol does not have a double bond. Therefore, my bromine will not break apart. And when I add bromine to that alcohol, my red color will stay. So this gives me an idea if I made cyclohexene or not. All right, so let's go back to the PowerPoint. And here is what methylene chloride looks like. So it tells me to add 20 drops of methylene chloride, 2 drops of my product. So here are my test tubes. Test tube number 1, this is my cyclohexanol. Test tube number 2, that's going to be my cyclohexene. And test tube number 3, that's going to be my product. So here are all 3 of the test tubes that are full. They are ready to go, and I need to add my bromine to it. So once again, cyclohexanol to the left, cyclohexene we know for sure in spot 2, and then the one to the far right is the product that we've made together. So here are the test tube and the test tube rack, and I'm getting ready to add the reagents. So in goes the bromine. Take a look at what happens. That's me trying to show you the bromine bottle, and that didn't show up very well, did it? So there's the first liquid bromine, there's the second addition, and there's the third addition. Wouldn't you know it? Look there! That's real life organic happening right in front of you. And all of those reactions we talked about in Organic 1, folks, here's one of those prime examples of real life utilization. So the one to the left stayed brown because bromine's still together. And then the second one and the third one, the 2 on the right, those went colorless. And now you know how to chemically explain why they went colorless. So here's a picture, a better close-up picture maybe, of the observations that we have made in the bromine addition. That is a qualitative test that we can make some observations on, write that down onto our data sheet, and this is going to help us prove what type of product that we have made in the end. All right, so there's test number 1. All right, so or test number 2, actually. We skipped number 1. All right, next, it's going to say utilize refractive index. So if you've had me for Chem 251, you know what refractive index is. If not, again, I'm not going to take anything for granted. Refractive index is this concept that I can put something on a prism and I can shine light onto that object, and that object is going to bend the light a certain way. Okay, and this is what we call the angle of refraction. So again, imagine yourself in a pool. The top half and the bottom half does not match up if you're standing on the sidelines looking down at someone. So this is refractive index pretty much. So liquids have refractive indexes, and we can use these values to help prove the products that we have made. And it's telling me that water is 1.3329. Cyclohexanol is 1.4650, and cyclohexene is 1.4460. So this gives me a couple of numbers to go by, and now we need to talk about refractive index, and we need to do that test. So this is what the refractometer looks like. Right here in front and center, that is the light source. That's right there. I can see it on. And then this eyepiece up here at the very top, that's the piece that we're going to be looking through in order to get our measurements. On the right-hand side of this instrument, we have a main adjusting knob, and that's here. So this allows me to dial up or dial down and allow me to adjust the settings in order to get the proper readout. So that is what we're going to be turning in order to get this aligned up before we make our reading. And then over on the left-hand side, you're going to see a display switch. And this switch, I'm going to push down when I get ready to take a reading. It allows my meter to show up. So that's really the only 2 things that I have to worry with this instrument. Pretty simple. So what you're going to see in this video is basically me getting ready to load up the sample on the refractometer. So there's my prism. That's a surface that we're going to put our compound on, and that surface needs to be cleaned. So we clean it with acetone. It's a very good solvent in organic chemistry. So it just helps make sure there's no residue, no contamination on it at all. And here I'm getting ready to run cyclohexanol. So I'm going to show you how hard this actually is. So I'm going to unscrew the bottle of cyclohexanol. We'll put just a couple of drops. That's all that it's going to take. A couple of drops on the refractometer prism. You're going to see 2 or 3. 1, 2. And I changed my mind, and I went back for 3. And then we're going to close the prism, and we're going to raise the lamp back up to that prism. And now I'll look through the eyepiece. Folks, that's as hard as it is to run something on a refractometer. Nothing more complicated than that. So when I look through that eyepiece at the top, this is what I'm going to see. And I'm immediately going to notice a division line right here. I mean, we see that go all the way across, right? So this is a very light area, and this is a darker area. So the goal here is to use that really big fat knob, this knob over here on the right-hand side, and I'm going to turn that knob until I get that dividing line right here in the center. That's where I want it to be. So once I line that up, I'm then going to go back, and you remember the flipper switch? I'm going to flip that switch down, and I look through the eyepiece, and this is what I see. Magic! So it goes from this, and I flip the switch down, and it goes to this. So this way you can read a value for refractive index. If you have never read a refractive index before, folks, this is how they are divided up. Notice that this is 1.45 and this is 1.46. All right, so the way that we read this, 1.450, 451, 452, 453, 454, 455, 456, 457, 458, 459, and then 460. All of the tiny little tick marks in between are going to be halves. So 1.4500 is actually that first reading. This one, the taller tick mark to the right-hand side, that's going to be 1.4510. And that little tiny one in between them, they're always halves, which means that little tick mark, if that's where it was, if that's where my reading was 1.4505. So 05 and then 451. 4515, 452. 4525, 453. 4535, 454. It's always that 5 or 0 at the end. All right, so where does the number get read? Well, it's the crosshairs, folks. That's the purpose of the crosshairs. So this line that you see goes straight up and down right there. This is the value that you want to read. So if you need to, pause it, read the meter, get an appropriate refractive index readout, and that represents the refractive index of cyclohexanol from our stock. Next, I did the same thing with cyclohexene, and this is what we get here. So once more, pause the video if you need to. Look at this meter. Try to read this value, which is going to be right here, and report that number. And then the next one is going to be product. So once more, pause the video if you need it. Read the meter. There's the crosshairs. So that line that goes straight up and down, folks, that's what we're after right there. And now you have three values, and you can compare those three values. So does your product closely match the cyclohexene, or does your product match the cyclohexanol a little bit better? That's up for you to determine, and that's going to be part of the questions at the end of the lab. All right, so finally, if I go back to the lab procedure, it's going to say, use infrared to compare cyclohexanol and your cyclohexene product. Okay, so that's not a problem. We have something called an FTIR instrument in the lab. So this FTIR instrument is a little bit fancier than your run-of-the-mill infrared that you might find in a traditional laboratory setting. So if we want to show you a video, I can. I've got one ready. Why not? I'll just sit back, relax, enjoy the show. So here is our refractive index, or FTIR. So this video, our laboratory technician recorded for you. Here is the software on our computer that operates the instrument. So you're going to see the mouse go over, and she's going to double click this software application to get this instrument initiated in just a few minutes. Here's the opening. This is where our sample is going to go eventually, but we need to initialize and we need to start the machine up first. All right, so we're going to double click on the software, and this is going to open up the software platform and connect the computer to the FTIR. FTIR, the F stands for Fourier, and the T stands for transform. Fourier transform infrared spectrometry. Doesn't that make you sound fancy and smart? Otherwise known as FTIR. All right, so there's going to be a little bit of delay here. That's normal, not uncommon. The instrumentation and the software is a little sluggish. You pay, $50,000, $60,000 for this piece of equipment, and you get this type of setup. So not unheard of. This is where your money goes, folks. So we hit OK, and that initiates the software up. And the very first thing that we're going to have to do is go in and get a spectrum. I mean, that would make sense, right? We want an infrared spectrum. It told me that in the procedure, so we're going to hit spectrum. And then this will open up the home screen, and it's very much like tearing out a balance. When we use a balance, we want to make sure we go over, we hit the tear mark, and it reads 0. And that's exactly what we're going to do here as well. So we're going to go over, we're going to tear, quote, the FTIR. And then when we do that, this gives me a background, or what will set me up to do a background at least. So the very first thing that we're going to do is go into instrument. You can see that right there. It's kind of fuzzy and out of focus, but again, I blame the camera for this. We're going to hit the drop-down box, and we're going to go to what we call initialize. So this will initialize the software to communicate with the FTIR instrument. So I think our laboratory technician here was fumbling around with a zoom to try to get it to look a little bit better for you, and it was just no hope. She was fighting a losing battle. So this is getting rid of the old data. Yeah, we're going to do a new background here. So now she's initialized, and you will see these 3 green buttons at least appear green when it becomes ready. So the initialization process takes a few seconds once it's initiated, and you'll see those pop up green. I'm going to hush for a few seconds. Can you believe it? I've been talking for over an hour. But keep in mind, you would still be doing your distillation setup at this point. You haven't even made it to the last step of the FTIR yet. Again, it's all about you, folks. I'm saving you time. Look at this. All right, so the 3 green buttons are go. And that means the instrument is now ready. All right, so what we have to do is we have to pull out an attachment. And this attachment is called an ATR attachment. And that ATR is attenuated total reflectance. That's what that stands for. And this is basically $18,000. All right, and it's not this actual piece that's $18,000. It's this little disc right up here at the very top. That's $18,000. And not just the metal piece, but in the center of this is a little bitty speck about that big. And that little bitty speck is $18,000 because that's a synthetic diamond that this machine runs off of. All right, so here's the side view of that ATR, and we have to put that into the instrument. You can see the infrared energy that's getting ready to be delivered into our sample, and our sample is going to be delivered on top of that ATR attachment. And folks, you can see that. Look at this. It's right there. 18 grand right there. Okay, more than most people's cars, and that's right there in that little disc. So we're going to put a few drops of that solution and my cyclohexanol and the cyclohexene, including my product, onto this thing, and we're going to run them separately just to compare the different infrareds that show up. So loading samples, folks, they're very, very easy. It just takes a couple of drops, and that's it. So in this video, we are getting ready to do a background. That's what we're getting ready to do. So before I put a sample on it, I kind of skipped ahead a little bit, but we're going to background scan with it completely clean. Again, it's like tearing out a balance. I mean, that's what the purpose of this background scan is for. So clean, nothing on it. We get a signal. This is common, not a big deal. And it's going to take this signal and it's going to subtract it from the signals that we get from the things that we run on it. It's just like tearing out a balance once again. So this process is going to go forward. My buttons become 3 green again. So once this process completes, we're going to go back up and we're going to hit measurement. So this allows us to measure samples. I get my 3 green buttons. I put my couple of drops onto that disc that you saw just a few seconds ago. Our laboratory technician's going to go in. She's going to name it, so that way we can keep track of what is what when we print off the reports. So she's going through. You can't really see it. Again, it's fuzzy, but she is naming these spectra that she's going to be generating for you. And once she names them as a data file name and a name that will show up on the report, then she will go and she will hit the big green button that says Sample Scan. And that's right there in the center. All right, so we're getting ready. She zoomed back just so that you can see while she's running. And in this case, she's going to be running cyclohexane. Again, it's very fuzzy. It feels like you're drunk, I know. But again, that's the camera for you. It's not zooming automatically. So we're running cyclohexane. And she's going to take a couple of drops of that stuff, that reagent. It's going to go onto the disc. 18 grand right there. Couple of drops. That's all you need. And then she's going to go back to the software. And the software, she's going to hit Sample Scan. There you go. So this is going to take about a minute to a minute and a half. So she's going to stop the recording, but you can automatically see an infrared signal that shows up. So what do these lines mean? Well, to be honest with you folks, you don't know that yet, but you will know that by the end of this semester. So we're going to start talking about these infrared spectra, and we're going to talk about why and how and what they mean. So be prepared. It's coming, and it's going to be coming very, very soon. All right, so there is the way that we check or run a sample onto the FTIR. Once it gets finished, there's one more trick that we can do, which is one of the reasons that we paid 50, 60 grand for this instrument in total. In the software, we're going to go up here to this thing called Search. You can see a pair of binoculars right there. What Search will do is it will allow you to search that signal that you got from your compound into a database of tens of thousands of compounds that we have. So the spectrum search is what she'll push, and within a matter of seconds, it's going to say, bing, this is what this material is probably going to be. Based on the signal that we receive from the instrument, this is probably what your sample is, and it will give you a name. So it will give you the top 20, and that's what you're going to see down here below. Sometimes it does a really good job, and sometimes it doesn't. It misses it a little bit. And here is a screenshot of one of the samples that she analyzed. So this is going to be the product, and this, this is the cyclohexene stock. You can see that name up here in the top right-hand corner. And that stock is going to have cyclohexene as a name down here below. So here's the thing that you need to do when you download the infrared spectra, because we're going to upload them for you so that way you can compare and contrast. You're wanting to compare the shapes of the infrared spectras with each other. So you'll have one for your product, you will have one for cyclohexanol, and you will have one for cyclohexene. What I'm going to do, though, is I'm going to get rid of everything that's down here below. I'm not going to let you see those names. I want you to compare and contrast the different infrareds to see which one this matches up closer to. And then that way you can identify that and write it into your lab paper that you'll submit to me a little bit later. All right, so that's it of the lab. That's all it was. So 1 hour and 13 minutes, and we basically did a 3 to 4 hour lab experiment in that amount of time. So you came out in the clear with this. It's good for you. Look at that. So a couple of things I want to talk about at the end of this lab document. Page 14 that you will get. There's a couple of post-lab questions that I do want you to answer. So first, number one, calculate the percent yield that you obtained from this reaction. So take the grams of cyclohexanol, and then you need to calculate the theory gram of your cyclohexene. So you need to use a little bit of stoichiometry for this. I'm not going to go over that because that's Gen Chem stuff. You should know how to do that now, folks. So gram of one substance, gram to another substance, you need to use stoichiometry in order to calculate a theory yield. Once you get your theory yield, you will have an actual yield. You know that because I showed you the mass numbers. And you will use theory and actual to calculate the percent yield from this experiment. Number two, we're not going to do because we did not do that test. Number three, did your product cause a color change with the BR2 reagent? Why? We talked about that. Number four, compare the infrared spectra. And what evidence do you have that you made cyclohexene as a product and not cyclohexanol? Explain. Number five, it says calculate the refractive index of your product at 20 degrees. This is a correction factor. Don't really want you to do a correction factor. This is unnecessary, so we're going to cross out A. The reason they wanted you to do this is because the refractive index values that they gave you were based at 20 degrees. That is why we ran our own stuff. So you have refractive index at our room temperature of cyclohexanol and cyclohexene both. That's what you need to compare it to. For B, compare the refractive index of your product to data table. Is it pure? Why or why not? C, if the refractive index of your product differs, why do you think it did? Number 6, what would be the major product obtained from a E1 dehydration of 2-methyl cyclohexanol? So that's like a theory question. Number 7, outline a mechanism for the dehydration of 1-methyl 1-cyclohexanol. Do you think it would go faster or slower than the reaction that we did together in here? So these are the questions I want you to answer at the end. And then there's also pre-lab questions. Now, I know you should do them before lab, but you probably didn't. But I do want these questions answered as well. So number 1, what safety precautions should you have taken? Number 2, write the chemical equation for the reaction that happened. For B, using the following information, calculate the theory yield for 3 mils of cyclohexanol. So there we go. Number 3, when 2-butanol undergoes dehydration, 3 alkenes are made. What are they? And which one would be the major product? So folks, that's a wrap. This is the dehydration of cyclohexanol, your probably very first lab experiment in Orgo 2. So if so, congratulations. Welcome to the class. And some of the other labs will be very similar to this structure. Other labs will be more of a handwritten laboratory journal that you will turn in for me for grade. And we'll get to that point when we get to that point. But for now, here is dehydrating cyclohexanol. Once more, you got it done in 1 hour and 17 minutes instead of a 3 to 4 hour lab class. So good for you. I wish you luck on the questions. You don't need luck. You know this. You got this. It's like the back of your hand. I know it. And everybody will give me a 100 on this lab experiment. I know you will. I can feel it. If you have got any questions, you know where to find me. You know how to get in contact with me, so do it.